Okay. But I think we're all set. Can everybody see the screens okay? Or is there anybody that cannot see them okay? I could try and adjust the lighting, but I don't. The idea is to have like you guys lit and this dark up here, but maybe not. All right. So uh all good here. Okay, perfect. All right, so yeah, welcome to COMP2402, data structures, algorithms, and data, abstract data types and algorithms. So basically, it's a data structures class. But of course, algorithms are closely tied into that. All right, so let's talk about the course, and then we'll go into some introductory stuff. And well, basically, this is yeah, it's a class on algorithms. It's a compressed course, which is going to that means that the requirements, the amount of work that you're putting in per week is going to roughly be double. And it means that once this week is going to be kind of slow, but after this week, it's going to be kind of relentless. You'll have either an assignment or a midterm every week after this one, as well as labs. But to start with, how we present the class, well, lectures are given live and in class, but also recorded over Zoom, as you may have noticed. Right, I want to give maximum flexibility. These are long classes, and it's summer, so it's going to be kind of warm in here. And I get it. If you want, whatever you want to do, however you want to consume the class, it's up to you. I like to present, I like to give you guys the options. I get a lot out of recorded lectures when I watch a lecture. It's nice to be able to sort of skip the parts that I'm not interested in and focus on the parts that I am. So I like to give that to you guys as well. But I also like to, it's nice to have students here participating. TA and instructor office hours will be posted very soon, right? So technically, I think we have decided to go ahead with, although it's not officially on Brightspace, but office hours will be right after class, Tuesdays and Thursdays,
अपने भाई को फोन
2
तेरा भाई
hours.
तो खाना खा रहा था
So that'll be me and
करते
there's
हैं रुक जा
of course,
हाँ
they're
कर
both
देखती
very
हूँ मैं
good.
कितना करता हूँ
And so
एक
yeah,
फोन तो दे
so
दे
everybody's on location.
अरे
This
मैं
is sort of where you're
बाथरूम
supposed
जा
to
रहा हूँ
be.
यार
एक सेकंड
After class, if you need help, we'll be here for you in this room, right? So then it's just easy. If anybody cannot make it, right, particularly the people, I guess, over Zoom or whatever. Oh, mutes, yes. Please let me know as soon as possible, right? So if you need some outside hours, let me know, and I'll see what I can arrange. But we are sort of, we're running on a minimum crew this summer. The people are very competent, but there's only 2 TAs and myself, so we cannot cover everything. So in order for everybody to make the most use of it, it will be after class. What else? Of course, there's Brightspace. There will be forums that will be put up on Brightspace for you to ask questions. Assignments will be programmed using Java, and hopefully we have a submission server up, and hopefully that works. I've not like stress tested it. I've tested it, but we'll see what happens when 150 people start trying to submit their assignments. If worse comes to worse, like we're going to, yeah, I'll get to that in a sec. But yes, if worse comes to worse, right? If the server doesn't work for whatever reason, just take a screenshot, send it to me. We'll work it out. All right. Nobody's going to be penalized because of a hardware issue that we just can't. We can't put enough throughput through our OpenStack instance. So yeah, just if something goes wrong, take screenshots, send me an email right away. But yeah, I'll go over a little bit more of that shortly. Labs are small open book mini quizzes hosted on Brightspace. So traditionally labs are, yeah, well, I mean, they're exactly what they sound like. They're very low stakes. You can take them as many times as you like. If they're not set up exactly that way, please let me know and I'll fix it. But it's easy marks just for engagement, right? Just, I want you to sort of, in the summer, there's a chance of like disengaging from the material, right? Like it's just, oh, I'm out doing this or that, which is sort of natural. Why are we using a server instead of Gradescope? Ooh, that's a good question. Because we're broke. We can't afford Gradescope. That's it. We decided to go with another. So Gradescope was a trial basis, and we've gone with something else called Assign2 for now, at least, but it does not have submission server, does not have programming assignments. So, actually, submission servers are something that we've done here before, like I've done them before, particularly with this class, hosted here at school, and so we're going to try that again. I've never done it with OpenStack per se, but in principle, it should work. All right, there shouldn't be too much of a difference. Discord. Yeah, okay. So questions on Brightspace. Obviously, you can email me for questions that maybe are more of a personal nature, but if it's in relation to class material, I prefer you post the questions on Brightspace. We're going to put up the forums. And then of course, when it's answered, then everybody can see the answer. Sorry, what was the other part of that? Discord. Students typically like a Discord. It's hard to police a Discord. So if you want a Discord, it's going to be an unofficial student-run Discord. Okay, so, and you guys are free to do that, and I will post the link on Brightspace if you like. But what I don't want to have to do is police it and make sure that everybody's, you guys should all behave yourselves, but it's just, it's not the best forum for you guys to post questions and me to find them, right? There's a lot of chatter on Discord, which is great. If you're socializing with your peers, that's fantastic. But it's difficult for me to find out which questions I should answer. Brightspace is a lot better for that. So if you want to have a Discord, I will post the link. If somebody wants to set one up, email me the link, please. And I'll post it on Brightspace. And then, I just ask that everybody is respectful. If it's a student-run Discord especially, please be nice. Assignments. So there's 4 assignments. Labs are, again, they're the low stakes. Just keep you engaged with the material, maybe sort of remind you of the things that you're supposed to be thinking about, and get those marks in. And I like typically to offer bonus marks either on assignments or labs, probably both. The idea being is I hate getting emails at the end of the semester of, can you boost up my grade by this much because I want to get to the next letter grade. Well, I'm going to give you the opportunity to do that for yourselves, okay? So there'll be bonus marks available. And if you at the end of the semester, if you email me about boosting a letter grade and I see that you haven't done all of these things, these extras, then, well, I don't know. That's on you then, right? I can't, I'm not going to boost your grade in that case. Bonus marks with WooClap. Ooh, that's another good question. I completely forgot about WooClap and trying to get the server up and everything else. But yes, it's possible I might do that. Probably, right? WooClap's nice. Thank you for reminding me. So possibly there will be bonus marks associated with your WooClap. One midterm, one final exam. We'll see the, well, let's take a look at it right now. The calendar looks something like this. All right, so there's an assignment 1, part 1. That's due this weekend. Very, very simple. You download the file from Brightspace, you submit it to the submission server. It's going to ask you for a secret code, so you have to put in your student number. It will email you your secret code, and then you submit it, and it should give you a 0. And that's fine, and everybody who does that will get 5 marks for the part 1 of assignment 1. Okay, so what I want is, if I don't do this, traditionally what happens is that when assignment 1 is due, Sunday night at 6 o'clock, I get a ton of emails of people just not knowing how to submit their assignment, right? So this is just 5 marks. It's the assignments out of 45 altogether. 5 of those marks are for submitting anything to the server by this Sunday. And then, so after this week, then next week, things start in earnest, all right? So we have tutorial 1 due here, and at the end of the week, the full assignment 1 is due. And then after that, the next week, assignment 2 is due, and then the week after that is the midterm, and then assignment 3 and assignment 4. Okay, so it's going to be very busy. after this week. This week we'll ease into things. All right, questions on that? All right, so let's look at, well, what are these things worth? Well, first of all, this is based on Pat Morin's reference textbook, Open Data Structures, right? It follows it very closely. This is Open Data Structures is a very math-heavy textbook, but we're going to try and take a light view of the math. I want you to understand these things, and you can prove a lot of things mathematically, but I don't want you to get bogged down in those. There is a laptop requirement if you're in second year, or any year really at this point. You must have your own laptop, and it should meet some minimum specification. Basically, all your stuff, like the Java that we're going to use, I am usually Java 8 and beyond, you should be fine, right? What we're using for the programming assignments is very low level. It's the part of Java that very rarely changes. So you should not run into any trouble. If you do run into any trouble, compatibility issues or what have you, just let me know. But by and large, Java is easy. Install some Java, it's probably fine. Okay. Reading exercises in the textbook mandatory. Lecture slides should be enough. The lecture slides should be enough. Go to the textbook if you're confused, right? Or maybe if you like Pat's style of writing, for sure, it's a good resource. But yeah, you don't need it. I like to be very, very upfront about the things you need to know going into a midterm or a final exam, right? I'm not trying to fool anybody. There's no tricks. I'm going to tell you basically exactly what's on those things. And then it's up to you to study and get them correct. Okay, so I will let you know before a midterm, or the final, what you should know going into it. All right. But basically, 50% are the tests and 50% are the assignments. The tests have to be in person. Okay, there's no remote tests. I mean, if you are out of town, there are things you can do. You could pay like $100 or something to have somebody watch you take the test, right? We have an agreement with other universities, so that is an option. If anybody's on vacation during the midterm or, heaven forbid, final, you should be here for the final, but there are those options. You do have to pay money, but I do not accept co-mass. It's just not secure enough, right? I want to see you sit down and do the work, or somebody sees you sit down and do the work. Marks will be posted on Brightspace or available on the submission server, right? As you submit your assignments, it'll keep track of. I had it set for 20, and then I rolled it back to 10, so it'll save your last 10 assignments. And the highest mark out of those will be the one that is recorded. That's a good question. So what is this? So typically, I think I'll have to get back to you on that one. I think a D is sufficient for a lot of classes. If you have a D in this class, I believe you can take 3804, but I will have to double check that. That's a good question though. All right, so midterm is in class, in person. Late assignments and labs are never accepted. I mean, we have to draw the line somewhere, right? But I'm not, it's the summer, I'm less busy. I can be slightly more flexible. Is it a C minus? Okay, well, I could be wrong, yeah. But not too much, because the submission server, I have to basically take down assignment 1 to put up assignment 2 at this point, right? I haven't developed it enough to get any fancier than that. So I do have to put a deadline up so that people can get started on the next assignment. The final exam be multiple choice. Will be partially multiple choice and partially like written answers, possibly written coding, and or drawing pictures of data structures, and or drawing some representation of a data structure, whether it's a table or a tree diagram or something. So there will be a written component to the final. Yes, it does auto grade like Gradescope. I'll demonstrate it here in a second. So late assignments and labs are never accepted. Again, I mean, so the smaller the class is, the more you can sort of bend these rules, right? But I'm not going to bend them too far. Okay, so just try and get everything in on time. If you make a mistake, if you somehow miss a deadline, the key is email me right away with your assignment, all right? So the sooner I have your assignment in hand, the more chance you will have of getting it marked. Okay, if you just send me an email saying, oh, I missed the deadline, and you don't attach your assignment, and then I email you back, and then it's 3 days later before you email me, like, no. Okay, that's, sorry, I'm not going to mark that assignment. But so the key is just get it to me. I don't want anybody to get a 0 because they were 5 minutes late or whatever, right? Their internet went out or whatever. So I am sort of, you know, I do sympathize, but at the same time, like, just get it to me as soon as you can, and the sooner the better. So again, online, no, but again, there is an option, right? So you can pay, I think it's like $100 or something, to take it at another school, and somebody there will watch you. But they get paid to do that. So you should talk to, well, we'll look at some emails of people who you can talk to. Yeah, I guess also, like, this is a compressed course. It's a difficult course, eh? It's one of the more difficult courses in second year. 2804 might be the next most difficult. If you're working full-time, I just don't recommend that. Now, you guys all know your limits, so you're all adults, you're free to do whatever. I think if you're working full-time, you're gonna have a very difficult time doing well in this class, unless you cheat, right? I mean, there's always that, but of course, that's my opinion. You guys know your own limits. Again, you're adults, so, make your own decisions. That's just my advice. If you're working part-time, you should be fine. Academic integrity, collaboration. There's no collaboration on tests, but in general, yeah, man, talk to your peers about how did you solve this problem, right? I would never gotten through grad school if not for my peers, right? So you should not do this stuff in isolation. That's very hard. When you get stuck, it can be very discouraging. Ask your peers, ask myself, ask the TAs. You will not get in trouble for discussing solutions, ever. For copying solutions, yes. Artificial intelligence, I mean, let's just say officially you're not allowed to use it. Unofficially, I mean, there's no way for me to tell if you've used it. Unless your assignment has, like, I am a large language model, thank you for, here's your answer. Would you like anything else? Like, unless there's something, a smoking gun of evidence, there's no way I can determine that you've used ChatGPT. I can suspect it. I mean, there's a lot of evidence that you've used it, but there's no proof. So officially, you shouldn't use it. Unofficially, if it's in, I use it. It's a great resource for technical details, right? So I forget, oh, how do I write to a file in Java? Well, I just ask ChatGPT. It says, oh, yeah, here you go. And it's fantastic at that. It's really, really good. So yeah, if you're using it in the spirit of learning, that's what I would recommend. Sort of officially, you're not supposed to use it. The Zoom recordings posted right after class. Yeah, I try to, most of the time that will be when. Occasionally they'll be a little late, but I will be here for office hours after. So, after office hours, generally, I guess in this case, I will post it. Yeah, well, that's true. These are popular questions because they're nice and technical, and they're very, as you will find out, data structures are very unforgiving, and with good reason. Like, if your data structures have a bug, then every piece of code you run has a bug, right? So they have to run. they have to run fast, and they have to be correct. So they do make popular leak code. There's no official tutorials. There are office hours right after class. When I say tutorials, it means the small quizzes are due. Yeah, it's this. I call them tutorials. I changed it from labs because last time I used labs and that was confusing, and then I guess tutorials is kind of confusing as well. So there's no tutorial sessions. There are tutorial assignments, but they're easy, right? All right. Oh, office hours. There will be, yeah. So we have one TA, I think, especially for the first 3 weeks, one of the TAs will be doing online office hours, and one of the TAs will be joining us here at 2:30. And then, so that's the plan. And again, if those hours don't fit your schedule, please let me know as soon as possible. But yeah, office hours after class, myself and one TA to start with, and one TA will be online. So if you're not on campus, you can still come to office hours online. All right, yeah, you should spend at least 9. This is for a non-compressed course, so double that. There is a computer laboratory. I think there's like, I don't know, you have to contact them to find out the details. I believe they have laptops now. They're taking out the computer stations and then they're just going to hand you a laptop when you come in if your computer breaks down or something like that. But follow those links, ask them questions. The undergraduate academic advisor, these people are great for all, any type of advice you need. Am I taking the right courses? Am I going to graduate on time? Should I take this class this summer, etc. They have all these answers, so do email them. And then, 1406. 1406 is quite easy compared to this course, I think. But it's not, I don't want to, it's not an impossible course. It's not a course that you're destined to fail. It's not the honors killer that 3804 is, right? Although this is a good warm-up for 3804. It's just more difficult than almost everything else, except for 2804. And in particular, there's a little bit of math, not too much, but we do need some math for analysis. So this is not a math course. I will almost, I want to say never, but will very rarely test you purely on the math, right? It's always, the math is a tool that we use to analyze these algorithms and data structures. Well, you'll see. I mean, the two things that they find difficult are you have to have a very thorough and detailed understanding of these data structures, right? So if you're going to implement them, you have to understand them completely. And tiny mistakes have very bad consequences for data structures. So when we test you, we'll be looking for all of that little tiny technical details so that to make sure that you fully understand these data structures. And when you're programming these data structures, it's the same thing. There can be like, you can make one tiny mistake and get a 0, right? That can happen because these things have to run perfectly. The first thing we test for is correctness. And if they're not correct, then we don't bother testing anything else because, why bother? How fast is it? It doesn't matter if it doesn't work. So you're going to find that you can really write like 90% of it and then get stuck on that last 10% or 5%. And then you're getting 0 on the submission server, right? So leave yourself ample time for debugging, I guess, would be good advice. But the first assignment is sort of easier. So it'll be a good, if you're starting to panic about that, then give yourself a lot more time to do the second assignment. Second assignment is kind of difficult. I might make part of it a bonus. In addition to everything we talked about, of course, this is a university. You may be, some of you are not living at home, or maybe not even living, in the same city as your parents. There's a lot of resources here to help you out if for any reason, right? So there are some stuff listed here. There is more than this. I can provide additional links for anybody who is, you know, who sort of needs the help. Take advantage, right? I mean, the university is here to serve you, right? So, you know, if you need something, let us know, and we'll see if we can help you out. All right. Any more questions on the course outline? Okay. All right. Let's take a look at the submission server. Here it is. Nothing fancy. There's no. I mean, there's no name. It's just an IP address and a port number. This is on OpenStack, which means that if you're on campus, you can access it. No problem. If you're off campus, you need the VPN. So the VPN is required for this class, so please download it. Again here, so assignment 1, part 1, due Sunday, this Sunday. Submit anything, any file actually, I don't even care. Whatever you want to submit, just don't submit like a 30 gigabyte file, okay? I'm not set up to handle that. If you're caught doing that, you're in trouble, right? Because you're messing it up for everyone else. But submit any file, preferably download the file from Brightspace. Assignment 1, you don't have to touch any of the code. You can just submit it. It'll give you a 0, but it'll record that you submitted something. And then next Monday, I'll run a script that's going to just go through and record everybody who submitted something. And you will all get 5 marks for the first part of assignment 1. And then the next Sunday, submit the rest of it. Code up the solutions and submit it. And so you can submit every 5 minutes right now, right? Because again, this has not been stress tested with 150 students, so we want to give ourselves a little bit of room. This number may change up or down depending on how the server is responding. What that means is that don't rely on the server for testing your code, right? Write your own tests. There's a bunch of tests in the ODS library, the Open Data Structures Java library. There's a bunch of tests you can run and use. Perhaps part of, maybe not this class, but next class, I will show you how to use them. So yeah, write your own tests. And then when you're ready, submit. And then you have to be very careful about the file, the naming conventions, right? So when you download it, you're going to get a folder. In that folder is going to be those Java files. Modify the Java files and then zip up the folder the exact same way that you received it and submit it, and that should work. Yes. So we no longer have Gradescope. We've switched to something called Assign2, and Assign2 does not have a submission server. Yes, Gradescope was great. I really liked it, but it was too expensive apparently for what we were getting out of it, I guess. I don't know. Well, Carleton is having a bit of a budget problem, as are every university in Canada. So yeah, we are sort of budget conscious right now, and it was too expensive. Yeah, the sign is very beautiful. We had a choice between that and Gradescope, and so I hope you like the sign. All right, so first thing you want to do is put in your student number and email me my secret code. Here it says the student number not found, but if you have a student number, if it says that, if you've entered your student number correctly, let me know. I will have to update the CSV file a couple times as if people join late. But if your student number is on file, then you should get an email with your secret code, and then you take your secret code and you enter it. So in this case, I want to submit. That's my secret code. I want to choose a file. I mean, I can choose basically anything and then upload my assignment. And here I got an error, no directory named COMP2402A1, right? So as I said, The sort of file structure that you download, you should keep for when you resubmit it. So in this case, now I have a special account where I'm going to have to change my password after this, or my secret code. I have a special account that I don't have to wait 5 minutes to submit again, right? So, but what I can always do is check my grades. So here you can see that the last 10 or 11 assignments I submitted, it's supposed to be 10, but there's like, depending on what you do, you might have an extra one there. But you'll have 10 or 11 of your previous assignments, and then the highest among these will be your mark. Okay, so here you can see I got 40 out of 40. So even though this one was a 0, I would still get 40 for this assignment. All right, you don't have to choose which one you want to submit. It'll just take the highest. Yeah. Okay. Yeah. Right now it's entirely auto graded. That could change. I've had I know Robert's doing something different, and we may do something where like also give us an analysis of the program you wrote. But mostly it will be mostly auto graded. Yeah. Other questions? Okay. Let's see if I can find my solution here. Okay. So here you can see it. So it's chugging. Now it's very, I vibe coded this, right? So I mean, I've written servers before, but I've never used Node, and this uses Node, so it's not the fanciest. All right, so just bear with me. But so you submit it, you wait a little bit, it'll time out if you wrote an infinite loop or something like that. Here I got 35 out of 40. Whoa. Where did I lose marks? Program is too slow. All right, I think I have to adjust that. A really long time. All right. If you think the speed stuff again, so if you have any problems whatsoever with the server, please email, bother me with it. Don't be afraid, even if it's kind of small and you think insignificant. I really want to get the bugs out before the deadline in 2 weeks. Okay, so if you get something like this and you're like, oh, it says too slow, that doesn't seem accurate, like I'm just barely missing this, like let me know so that I can make the adjustments. And again, be patient. Although I'm usually very strict about deadlines, I get that we're working with a new server and there might be, your code might run slow because 10 other people are running code at the same time. So I don't want to penalize people for that. So just take a record, right? Copy all of this, send it to me in an email and say like, I think I should get marks for this. And I'll take a look at it and let you know. Okay, but yeah, 35 out of 40. And then if I go back here, C grades, you can see that it's recorded 35 out of 40. All right, questions on that? Yeah.
It's a solution that part 2 could it show us what the actually graded or not yet?
I'm sorry?
If we now submit the solution to part 2, will it show, will it grade it now or no? Not yet.
Technically this is part 2. So part 1 is sort of unofficial. Like it doesn't show you the mark for part 1.
Show will it actually grade the assignment if we submit the solution?
Oh, right now? Yeah. If you get it right now, you'll get the mark. Yeah, you'll get. Oh yeah, you'll see exactly. If you, if you write it early and submit it, yeah, it'll do exactly this. Yeah, it's ready to go. Yeah, at this point. Well, there might be a few. Again, it's not been stress tested. Okay, so if it's running, if it's taking 10 seconds to run on the server and it takes like less than a second to run on your machine, let me know. Yeah. Sorry, you have a question? Yep. Yeah. Feedback is, I mean, loosely speaking, you get feedback, right? Sometimes it throws an exception and you can't figure out why, but yeah, it'll show you, if there was an error, actually, it would show you, no, not here. If there was an error, it would give you the, like if your code threw an exception and crashed, it would give you what your code output and then the error that was generated. So I try to give you as much information as I can. But yeah. Other questions? All right, should be. If this doesn't work, right? If Gradescope can't handle this kind of traffic, or not Gradescope, but OpenStack, then you will submit to Brightspace, and I'll just run a script at home. That's not as great because this way, at least, you know right away what your mark is, and you can just, once you submit it and you get a 40, you can relax, right? So I think that's kind of nice and worth the, slight number of headaches you might have while we fine tune the server. All right. Question. Yep. Sorry? Here? Secret code. Yeah, so I have my fake secret code here, but you will have, do I have a real secret code? I don't really, I don't really want to show you guys my secret code. But yeah, so you will get something that looks like, you will get something, I mean, it's just a hash of your student number and name and then a secret phrase that I use so that you can't reproduce it. And so it's like this 64 character long string of like random symbols, right? So your secret code is going to be something, you won't be able to like write it down like this. You'll have to copy and paste it from your email. But you can use this, you don't have to go digging through your old email. You can get a new secret code sent to you anytime you want to submit. You'll get an email, you copy it from the email and you paste it here, and then you can choose your file, upload your assignment, and then it'll verify who you are. And yeah.
Secret code different for every assignment, or is it just like each student has their own code?
Yeah, each student has their own code. It'll be the same for every assignment. Yeah. Other questions? Yeah, we've done like almost exactly this before, just not on OpenStack. So this is we'll see how our hardware holds up here. Okay. Should be kind of fun. I don't know. I'm excited. Again, just to reiterate, any small thing, discrepancy you have with your grade, send it to me. Maybe I'll say, no, sorry, this is, you have a mistake in your code. But I want to find ideally all the bugs before we hit the deadline and everybody submits at once. Yeah. Which IP? Like this address here? Oh, IDE? Whatever you like. So I guess I typically use, what is it? What's the popular one? It's not JetBrains. What's that? Eclipse. Yeah, I mean, you can use whatever one you like. I think I use VS Code just because I've been teaching C++ and I have VS Code available. But there's also IntelliJ. Yeah, that's the one I'm thinking of. IntelliJ usually works really well. That's what I typically use if I'm programming in Java a lot. Although I don't, you can use whatever, right? So you should understand, of course, a little bit about how to program in Java, what a package is, how you compile, how you run. Yeah, but yeah, use whatever you like. Okay, so let's start talking about the material. So I I like computer science a lot, and I think it gets sort of a bad rap of a bunch of boring people. Well, it's not. It's a bunch of actually very interesting people. So I like to open up with a quote. Vaughn Vernon, a software craftsman. I mean, that's sort of vague. But yeah, developers are, you'll find this a lot. There's a lot of places, right? When you go get a job or whatever, that I want to switch to the latest technology. And why? Well, because it's the latest technology. That happens a lot in this field. Here at university, we try and teach you the boring old technology, but the fundamentals, right? That's more important. Especially in an age of like large language models where syntax is not even really that important because I can always ask my large language model for the correct syntax. Actually understanding what's happening underneath your program is more important than actually, remembering syntax. So yeah, why data structures and algorithms? Well, increasingly code solutions and problems are made on demand, right? So we figure out what we want to do. We ask Copilot or ChatGPT to do it. Now, I don't recommend you doing this, but this is increasingly what's happening. However, this is how I built the server, incidentally, right? Again, I've built servers before, but not using Node. I had no idea what Node is. So I just sort of, I asked ChatGPT, like, here's what I want to do. It gave me some code, and then I run it, and of course it doesn't work the first time. But the fact that I understood what was most likely happening behind the scenes helped a lot, right? I said, no, like this is, or maybe I can ask for clarification. What is this function doing, right? You called this function, what does it do? ChatGPT explains it, and then I can fix my code. But I still understand basically what all of my code is doing. Even though like the syntax was just like, I don't remember a thing about Node. I'm just like, it was mostly generated and then I made some adjustments. But I still understand what's happening, right? The underlying models. So this class, we're going to be looking a lot at the underlying model, right? So it's increasingly important. It's still, even when you get your code generated for you, it's important to understand how it works together so that you can debug it and things like that. All right. So data structures in particular, well, all computers act on data. The data should be stored in an organized way, right? So if I open a file, that's data. If I do a web search, log into a social network, I mean, all of these things are transferring data. That's what a computer really is. It's a data processing machine. So how we store it and process it matters. What is a computer? Well, if you take 3803, you'll learn about what Turing machines are and things like that. But a computer is basically a general purpose computing machine. Not that that's super important, but what it does is it stores data, it loads data, it runs it through the CPU and transforms it into something else and then saves it again. So all the time that it's running, it's working on data. So how it accesses that data, right? So CPUs generally, they're so fast nowadays that we can't get the data to it fast enough to like slow it down, right? So the bottleneck is really how fast can we get data into the CPU? So how we store the data and how we access the data is increasingly important in terms of like how efficient and fast our programs run. All right. So a data structure for storing and accessing data. You might find that a lot of your problems are solved by just by choosing the correct data structure, right? So data structure and algorithms work really closely together. So I have a problem of access that's, it's too slow or whatever, but changing the data structure can often solve that problem. And that's basically the whole idea behind assignment 1 is you choose the data structure from the Java collections library that solves that problem for you, right? And so we're gonna go into a little bit of background of the things you should be considering as you're choosing these, and then we'll come back to assignment 1. But So imagine a modest data set of 1 million items, right? That's pretty small. And we look up each item at least once, and if it's not really organized, well, then we have to look through basically everything, or, on average, half of the things. So we're looking at about 10 to the 12 CPU operations to process that data set. If we look up everything at least once, that takes, a CPU runs at 10 to the 9 operations per second, and it takes about 1,000 seconds or 16 minutes, right? For 1 million things, that's a long time in computers. So that's not effective, right? So, and things like Google have tons of web pages. Now, a lot of these problems can be solved in hardware, but of course, if we can solve it in software, even better, it's cheaper. All right, so we need to be intelligent about storing and accessing data. And so the course is about, well, how do we think about data? What problems are you most likely going to run into? What are some common solutions? How do you analyze it? And yeah. So we're going to look at data structures. We're going to look at algorithms that operate on those data structures. Again, they're very closely tied. It's almost impossible to separate one from another. We're going to talk about the abstractions. So abstractions, you may have heard of abstractions in computer science, and they're the same thing in, well, so we're going to talk about data structures from largely a math perspective. That's the perspective that the textbook gives. And abstractions are the same thing in math as they are in computer science, right? It's a simplified version of what I want to do. I just have a function call. Any function basically is an abstraction, right? So if I say load file, that's a function call. It's an abstraction because behind the scenes there's a ton of complexity that I'm basically hiding. So I present an interface, and my interface forms a contract on what should be done. How does it get done? I'm less concerned with sometimes. And then we're going to analyze our algorithms and data structures. All right. So what's an algorithm? An algorithm is a sequence of discrete and precise instructions. We will look at pseudocode, pseudo-Java, basically. When we have to look at code in this class, it'll be pseudocode, but with like a Java flavor. Right. Mostly it's Java, but I can't fit. Java is very verbose, and I can't really fit it all on one slide often, so I just kind of shorten it. And then we're going to analyze this code using techniques that you learned in 1805 and a few new ones. So big O, also amortized analysis and probability and expected value. Again, these may sound very intimidating. Big O, you should know. You should be quite adept at big O. Amortized analysis, probability, it's good if you have a good intuition. You should be fine. So yes, we're using Java. Java is an object-oriented programming language, but it's nice enough that you don't have to worry about seg faults and things like that. And you don't have to release memory. It has a garbage collector. But it's still fine, you can still dig into the details enough to write efficient code. Yes, abstractions. I think we already covered abstractions. It's basically, we use them all the time, right? So I talk in abstractions. Everything I just told you at the beginning, the introduction to the course, is an abstraction to what we're actually going to do during the semester. So it's just sort of a generalization or a model. So sometimes when we talk about abstractions, we say that we want to hide the implementation details. It's very important to hide the implementation details. But sometimes these implementation details can leak, and especially with data structures, they leak, right? So when we have a list interface, a list on an array list or a list on a linked list, it's going to matter in terms of where we want to use one over the other. So even though we're sort of hiding behind an abstraction of the function calls, it's important to understand how the implementation will affect your code, even though we're kind of trying to hide it. I included this diagram because I think it's maybe the Oops. It's because it's one of the worst diagrams. I mean, I was looking up leaky abstractions, and this is the diagram I got, and I could not understand it for the life of me. I think I figured it out though. So these circles here are the cognitive load when I'm thinking. If I have to consider all of these implementation details, then I have a high cognitive load. So I hide them behind an abstraction, and then I have a low cognitive load, but then sometimes they leak, and then, I have a higher cognitive load. All right, anyway, that's this is as near as I could tell. I included it because I looked it up and I was like, I have no idea what this picture is. But yeah, I think I figured it out. We extract the data from the garbage collector. I don't think so. That's a complicated question. When the garbage collector runs, it doesn't, generally speaking, I don't think it deletes anything. It just sort of marks it as being able to, you can write to it again. So technically your data, after you delete it, is still there for a little while, but trying to hide. Yeah, no, you know what? Maybe that's not the best phrasing, trying to hide, but what we want when we have set up an abstraction is I don't want to think about what's running behind that abstraction. I just want, when I say load file, I don't want to think about all of the device driver calls that have to be made. Because that, it's very hard to think through all that. I just want to say like, this function will load a file for me. Same with a library, right? I load up a library. This library does a bunch of things for me and presents a nice abstract interface. So I say like, please library, go, extract all the characters from this PDF. How does it work? I don't know. I don't care. It's behind an abstraction. Somebody cares about how it works, but I don't have to worry about it. So that's what we mean when we say hide the details. It's like if I call my PDF library and said, give me all the characters from this PDF, well, there's a lot of things that have to happen. There's a lot of complicated code, but I don't have to think about any of it. Those details are hidden from me behind that abstraction. So that's what we kind of need. Yeah, exactly. Expose only the minimum details they need. That's a very good explanation. Expose the user to the minimum details they need to use the function. All right. So when we talk about a data structure, we look at the interface, which is like the abstraction layer. So this is what the data structure does. So in Java, we have a bunch of interfaces. They are explicit, right? So, and in a sense, when we talk about interface, the mathematical version of interface and the Java interface, we are really talking about the same thing. So interface is just, I define a bunch of functions that should work on this object or data structure in this case. Then the implementation, well, those are the details that we actually do care about in this class, right? So how does this data structure work? What does that mean in terms of runtime for these functions of this interface? And then, so once we write it and we're sure it's correct, we're going to analyze how well it does what it does, how quick it is, how much memory it requires. Right? I mean, those are the two big ones. I mean, all computers are essentially the same except for speed. Speed is the big, right? That's the big thing. When your computer is slow, it's kind of useless. So when we talk about analysis, we are often talking about speed, sometimes memory. Same idea. Those are our resources that we care about. So we're going to start with a simple example. We're going to make a data structure that's can add numbers and remove numbers. And so we're going to start by defining the interface. And we're going to go through a simple example, and we're going to look at some of the technical details we have to consider. Right? So the beginning of this class is we ease into this material a lot. So we're going to do a lot of examples that are not directly related to the data structures that we're actually studying. We're going to look at interfaces, and we're going to look at implementations. And analyze a couple of sorting algorithms, or maybe just one. But let's say that we have a data structure. We want to store data, so we can add a piece of data that is an int or remove it. And that's kind of unrealistic, but we'll stick with that for now. So that's our interface: add data, remove data. Then we have an implementation. So how are we going to implement it? Well, we have a couple of choices here. So, well, typically, I mean, we could just take a chunk of memory and store it in that chunk of memory all in a row. Right? That's an array. So I have my array. If I say new array in Java or wherever, I have basically some memory locations. Those memory locations have indices, indexes, whatever, however you like to prefer to say that. So these are the numbers of the index that represents the location in this array. And then I can put my piece of data, so 15, 17, and 3 perhaps. Okay, so, well, what are the things we have to consider if we're using an array? Well, it has a couple of benefits, right? Typically when I have an array, I have basically a pointer to the beginning. And so I'll say something like array, and then I'll use the square brackets and I'll give an index. So here I say array 1, and this uses what's called random access. So I have this beginning memory location. I add 1, well, however, an int in this case, let's say is 64 bits or 8 bytes. So I move to the next 8 bytes, but I can just compute that really quickly. So one of the advantages of using an array is I get random access, which means that I can jump to any location and tell you what the value is in that location in very quickly, right? Constant time. The problem is, as I'm adding things to my array, well, data structures are not always static. So I add some things to this array. Well, my array is static, right? The memory locations are static. So if I run out of space, well, I have to do things like allocate a new array, right? That's bigger, and then I have to copy these things over. So that is costly. Another thing I have to consider is, well, if I add something, let's say I add 23 here, well, that's fine. I can add it at the back, and that doesn't really cost me anything. I can do that very quickly. But if I wanted to remove something now, well, what happens is, well, say I want to remove whatever's at location 2, or say remove 3 is our piece of data. That's not a good number. Let's say remove 17. Okay, well, I go in here, I can delete it, I guess. I can set it to 0. But then I somehow have to record that that location does not contain data anymore. But what we usually do is we don't record that it doesn't contain data. We say, well, we just move everything over 1. So this is still, actually, these are still the same. But my data, 3, will get copied into here. And this 23 will get copied into here. So when we store things in arrays, in order to keep things simple, we like it when all the data is compact, right? There's no space in our array. But that means we have to do a bunch of extra operations when we say remove something from the middle or from the front. All right, so yeah. Something like this in Java is how we would allocate an array, although you will see that when we use generics in Java, you can't get away with this. We have to do we have to jump through a bunch of hoops. I'll show you how to jump through those hoops. I'll give you the code to jump through those hoops. We'll talk a little bit about it. But yeah, so what are the considerations? Well, I think we kind of just went over them. Here I have some space to go over those examples, but right, if I'm going to add, if I want to add to the back, so 16, 17, 18, if I say add 21, and I don't really care where it goes, well, I could just look at the next empty location and put it there. But when I want to remove a piece of data, of course, now I have some trouble where I have to close that gap. And also, if I use a different interface where I said, well, add this piece of data at a particular index, well, then I have to move things out of the way. So So those are some of the considerations. And when you're doing assignment 1, those are some of the things you should think about, right? So an array list is basically doing this. It has an array in the background. And when you add something, if you add something to the middle, it has to move a bunch of stuff out of the way. And if you remove something from the middle, it has to move a bunch of stuff to fill in the gap. And those, that takes time. On the other hand, another very basic sort of fundamental data structure is the linked list. This is a singly linked list. So what is a linked list? Well, I have, in this case, let's say I store some data 5, 7, 9. Okay. Where is it in memory? Well, it's not necessarily contiguous now, right? It's not all compact. It could be anywhere. That has certain advantages and some disadvantages. So I have 5, and then I have a memory location here, and this memory location is the location of 7, right? So I have a pointer to the next node that contains my next piece of data. So what sort of considerations do we have when we're using a linked list data structure? And yeah, this would be sort of the, again, pseudo Java code for making this. I would have a node that is its own class that represents this. This piece of data here would be this memory location, and this would be the next pointer that points to the next node. And then when I want to make a linked list, if I have a pointer to the node, then I can follow the sequence of pointers to get to any memory location. Right, so if I want to get what's in, this implicitly has index 0. So if I want to get what's at index 1, let's say, well, then I would start at the head, and then I would go to head dot next, and that would take me to index 1, and then I could return the piece of data that I find there. So what does that mean in terms of, well, in terms of our implementation? Well, first of all, if we want to add, well, in this case, my example, I'm adding to the middle, but if I wanted to add to the back, I would have to, let's say, well, let's just talk about general add. Maybe I don't add to the back. Maybe I want to add to the middle. Well, first of all, I have to walk to where I want to add to, right? So my linked list, I have a single pointer to the head. And if I don't want to add at the beginning, right, adding at the beginning would be kind of fast. But if I want to add somewhere else, I have to walk there first. Once I walk there, I can make a new node here, right? And have my data. And then I'm going to redirect a couple pointers, and I'm going to sort of stitch this node into my linked list. So in terms of runtime, we want to think about, what does that mean if I want to add to the middle of my list? Well, actually adding a new node is fairly quick. We move a couple pointers, but walking there to find the right location might take a long time. So we can use things like, especially if we want to add at the back. If we want to add to the front, we're all set. If we want to add to the back, we might want to keep an additional tail pointer as well. And then we can quickly add to the back and the front. Remove, well, actually remove is easy. If we have the node, we know which node we want to remove, then just redirect some pointers and we're done. Again, the big part of remove is finding the thing we want to remove. That's going to take the most time on a linked list. Okay, so when you're, those are some of the considerations for assignment 1. You can sometimes get away with stuff, right? Maybe you can get away with a slightly less efficient implementation than you should and still get the full marks, and that's fine. Nobody's going to come, nobody's going to double check that stuff. You want to add to the middle, just the head would work, right? We're actually going to go into a lot of detail about how to do this. Right now, I just want you to understand, right? Java does have an array list class with an array in the back, and it does have a linked list class. And then it has a bunch of other classes that are sort of tangentially related to those classes. And so when you're solving your problem, you should be thinking about these things, right? Do I have to add to the front? If I had to add to the front, then an array list, maybe not the best. right? Because I have to move everything out of the way in order to add. But if I want to add to the front and I use a linked list, that's going to work pretty good, right? So, and yeah, we have a lot of, these are very, very simple, but trees are generalizations of linked lists, right? The trees have nodes and nodes have pointers, and instead of one pointer to the next node, I have two next nodes basically. And so everything branches out. And hash maps are generalizations of arrays. Again, it's, I want to compute really quickly which index I want to store this thing at. And maybe my array has holes now, but still I have that a very quick access time. All right, 1241. So yeah, so those are some of the underlying technical details we should be concerned with. We're going to talk about some of the interfaces that you will see and use in your assignment 1, and then we will take a 10-minute break. So some of the common interfaces, well, the first one we're going to look at is the queue interface. Java has a queue interface, right? It consists of, well, maybe not exactly add, remove. They may have different names for these things, but essentially we have an add, add a piece of data X, and we have a remove, which removes, well, it doesn't say which one we remove. So which one do we remove? Well, that depends on the queuing discipline, right? So a queue is something we can add things to, and how we remove them depends on what type of queue we're using. So one of the types of queues that we can use is a stack. It's a last in, first out queue. Now, we're going to talk about, so we were talking about the queue interface, and we're going to look at various instances of it. And we're going to look at the stack, and we're going to look at the priority queue. And when you're writing your code in Java, right, these are interfaces. So we're not saying anything about the underlying implementation. But if something implements the queue interface, then you should kind of assume that these things will run quickly, right? So whatever underlying data structure is being used, right, because they can use multiple different implementations. But whatever one they want to use, it's going to run quickly, right? So the interface should give hints about the implementation. So a queue, I should be able to add and remove fairly quickly. And if I'm using a stack, I should be able to add, you know, it's a last in, first out. So I add a bunch of things to my stack, and then the first thing I remove is the last thing that I added. Right, so here we've drawn it sort of sideways. I typically like to draw it, you know, you can think of a stack of dishes. When I want my next plate, I grab the plate off the top, and then I eat, and then I clean it, and then I put it back on the top. And then the next time I go to eat, I use that same plate. So whatever's on the top of the stack is getting used a lot, right? I don't grab plates from the bottom. So that's sort of a last in, first out queuing discipline, often known as the stack. And if we are, you know, often when we implement the stack, instead of add and remove, we rename these functions to push and pop. So push means I'm going to add X to the back of my stack, and pop means I'm going to grab the last thing that was added to my stack and return it. So there's another type of queuing discipline, the first in, first out. Same two functions, add and remove. We're ignoring size for now. That's sort of trivial. But now it's different, right? It's like when I get into a line at Tim Hortons or wherever, I start at the back, and then I don't get served until everyone that is in front of me gets served, right? That is a first in, first out queuing discipline. So the first people to get there get served first. The last people to get there get served last. And again, if you use a queue with this first in, first out, you would expect that add front works quickly and remove last also works quickly. A priority queue means I define the queuing discipline. So that means that, well, I have a bunch of pieces of data. Let's use letters, A, B, and C, but I also give them a priority. So this might be 1, this might be 2, this might be 3. And so when I say remove, I find the thing with the highest priority or lowest priority, however you want to measure these things, and I take it out. And then when I add something, I give it a new priority, and it, I do not get removed from the priority queue until everything with a lower or higher priority gets removed. Yeah. Sorry, you good question? Yeah, that's a good question. So you can, I mean, let's stick to, yeah. I suppose mathematically you have a total order, which means that two things have the same, but again, we're going to implement it however we like. But mathematically, we would assume a priority queue requires a total order, which means that I have two things, I can tell you which one is less than the other, always, right? Unless they're the same thing. But when we implement it, we can do whatever we like, essentially. So we can have a bunch of things with the same priority, and then we would just, well, then I don't know, then it might be undefined which one comes first. We would have to read the Java docs on that. Yeah, that's a good question, but does that answer it? Other questions? Okay. So yeah, one analogy for this is, of course, if you go to the hospital, they do not take you first come, first serve, right? If you go in and you're dying or seriously hurt, you get bumped up to the front of the queue, right? You have a higher priority. Oh, yes. So the question was, in a priority queue, is it required? What happens if we have two things with the same priority? And yeah, we really didn't define it here. I guess the best answer is that's kind of up to you as the person implementing it. It's also kind of up to us in the mathematical representation, right? I said we should define a total order, and then everything, the total order means any two things are able to be compared. But yeah, basically it's up to us what to do if two things have the same priority. A deck is a double-ended queue. So this is, I can add very quickly to the front, and I can remove very quickly from the front, and I can add very quickly to the back and remove very quickly from the back. Right, so it's a generalization of both the last in, first out and first in, first out queuing disciplines. And, you might think that why not just use a deck instead of a queue always? And I mean, these are good things to think about. Why wouldn't you? So our deck, we would have an add first, add last, remove first, remove last function. And those are kind of, right, so I can take any deck and use these functions and implement any type of queue that I like. Yep.
Access to those elements in the middle. For example, compare them with the sorted anytime or no, never.
So again, we're talking, it's a good question, because we're talking in the abstract here. So what we're saying is that we define an interface, and these are the only things we can do in that interface. But if you're implementing this in Java, you might have a deck interface. So you have these functions, and then you also might have a list interface. So the list interface, I can add and remove from the middle. Maybe it's a little slower to do that, right? But it still gives me the option. So yeah.
Deck, you would never want to access the middle elements.
It's going to be slow if you do that, typically, right? If you have something that is built to be a deck, built to be add and remove quickly from either side, and we're going to actually make a deck, so we'll see this, but yeah, it's optimized to do those things, and it's going to be kind of slow if we add and remove to the middle. Also, it can, yeah. There's also maybe good reasons not to do that if I'm using my deck in a very specific way, right? I can kind of ruin whatever organization I have by sort of ignoring by doing things that I normally wouldn't do. Anyway, we'll get to it. Other questions? All right. All right. It's kind of warm in here, right? Let's take a break. It's a little bit early, but maybe take what the heck? Oops. Yeah, just try and rest your brain. When we come back, we will talk about lists. So today, going to be kind of heavy duty. We'll try and get into some lighter stuff later. A lot of this class is heavy duty. So yeah. So at about 5 after 1, we'll resume class. All right. So 105, I'm gonna get started. I'm gonna start just by doing a little demonstration of some of the things you might want to do for assignment 1. Number 1, what I did is because I'm super lazy, I went to ChatGPT and I asked it to write me a Python script that will generate a bunch of random strings. And so you can specify the number of random strings and the length, and also the file that you're going to save it to. So I copied that into my right next to my directory, right? So this is the starter classes that you're given, and part 0.java, I believe, just reads in whatever I give it and then outputs the same thing. Okay, so I have my Python script, and I'm going to save 10 random strings to infile.txt. And if I look at, I've already run it. So infile.txt has a bunch of random strings for me with no duplicates. That's what I said. I don't know. You have to be careful with ChatGPT because it can make mistakes, but right, you say no duplicates, you might get duplicates. I know from experience. Last summer, I had exactly that problem. So be careful. But here, this is just a short file. You can make, you know, one with 1,000 strings, which you might want to test for speed. And then, well, if you remember your Java, so I'm, you know, I'm on Windows. So COMP2402A is the package that holds my Java files, and they are in that package, which means that when I compile, I want to do something like Java C COMP2402A1. So I have to be outside of that A1 package, right? I think. Well, maybe not. Maybe not for compiling. To run it, I have to be outside. And then part 0.java. Okay. And then I can say Java comp 2402A1 dot part 0, which will run it. And by default, it takes arguments from the command line. And then I forget how you tell it to stop. I would have to read the documentation, but we're not going to do that. What you can also do is give it the name of a file. So I'm going to give it in file.txt, and it reads it and spits it back to me and gives me an execution time, right? So that's, and then if I wanted to, well, put this to an output file, I would just add outfile.txt. And then if we look in my outfile.txt, it's generated. So you can do things like run small examples to look for correctness, and then generate larger examples to test for speed. All right. Yeah, so any questions on that? That's sort of 1406 stuff that you're going to have to use. And of course, you have to install Java, right? But Java's pretty good. Essentially any version that's somewhat, I believe the Java 8 was when Pat wrote the textbook, was probably what we were using. So anything Java 8 and beyond, you should be fine. Here I'm using Java 21, no problems. We're not using any advanced features here, just the very basics. And the assignment is, well, part 1 is just submit anything. Part 2 is, well, think a little bit about how to do these things. So here, read them in one at a time until you've read them all in, and then output them, but, output the second half first. Okay, and make sure it doesn't take too long to do that. Should be pretty straightforward. Read them one line at a time and output the current line if and only and if it's smaller than any other line read so far. So smaller with respect to the usual order on string as defined as string.compare2. We're going to get into that stuff either today or next class, right? Again, it's kind of a slow start. We have a lot of background to cover. So we'll cover what this compare2 function is. But, feel free to try all this stuff out. Output only the last 10,000 lines, 9,999 lines in the order they appear. If there are fewer than 9,000, so yeah, I have to keep a running tab, right? So as I read them in, I store the first 9,999 lines, and then as I read in the next line, I have to get rid of a line, right? Because we're going to be checking. This is one of them that is memory constraints. So we can run Java and say, like, limit the amount of RAM that you get. And so if you try to store all of the lines, it's not going to work on the server. Output the current line if and only if it is a duplicate of some previous line. So how can I check for duplicates really, really quickly? When you're done, what's that?
It's a set function.
Right, exactly. Set contains, yeah. So we haven't gotten to the set interface yet, but we will just after this. And again, the interface is a clue as to what will run quickly, right? So set has a find, and find should run very quickly on a set. We will learn exactly why, but for now, it's enough to know that it's good. Output all the lines in case insensitive sorted order. So here you have to sort and write your own sort of comparator in order to do that. Or maybe not. There's probably other ways to do it. Output the current line if and only if it is not a suffix of some previous line. Right. So then now you have to do some string manipulations here. So suffix. So if I read in, what is it? Current line if and only if it is not a suffix. Yes, so if I read in this string and then I read in beef, well, beef is a suffix of that string, so then I would not output it. And yeah, and then the last one. Again, so you're going to read in a bunch of stuff. You're going to keep some current tally of the things. And then, yeah, anyway, questions on any of that? It's just practice with using, again, you don't have to understand the implementation super deeply, but you should kind of have some idea. Yeah, that's okay. Again, we're going to, because I'd done the demonstration, I decided to sort of explain some of this stuff. And yes, some of this is ahead of where we are in the lectures, right? So you technically have 2 weeks to do this part. So no worries, we are going to get to all this stuff. But it does yeah, it's a good warm-up assignment. Yeah, all right. Well, that's fine. Other questions? Yeah. I'm sorry, I didn't quite catch that. Sorry, I don't know. I'm old and like there's like fans and stuff. So yeah, so could you? Well, I mean, a good place to start is to think of what is the, you know, this is all computer sciences. You should start by just solving the problem and then make it quick. So, again, I may have missed some of the nuance of what you asked, but I think, right? So like if I read, what if I just wanted to solve the problem and I didn't care about speed? Read the input one line at a time and output the current line if and only if it's not a duplicate of some previous line. I just store everything in whatever, an array list. And then there's like a collection.find, or you can just run a loop over your array list. Every time I read in something, I say, is this thing in the array list? No. Then I add it. If yes, then I output it, right? That's it. That'll work. It'll be correct. It'll get you some marks. It just won't be fast, probably. So yeah, the first thing you should do is just solve the problem. Don't think about speed or anything like that. Just solve it in like the dumbest way you can think of. Just the most obvious, slowest running solution. And then at least that's my advice. And I'm sorry if I didn't. Does that answer your question or? Oh yeah, are there different yes. Okay, sorry. Yeah, so here we have a bunch of different classes, eh? So each one of these, the part one corresponds to, right, so your code goes here. See part 0 for an example. So part 0 just, I have a hash set. It's this doit function. So I add every line that I read in to my hash set, and then I print every line from my hash set. So you're going to replace this code with whatever, I'm going to read in certain lines and output certain other lines. Yeah. Yeah, each one is in its own class. Yes, that's right. Okay, sorry, yeah. Yeah, so you don't have to have a big if statement, which, for part 1, part 2, part 3, each one is its own file. Yeah. Assignment 1 is you should have sort of a working knowledge of how quickly these things can run and sort of what sort of problems you would solve with them. And then assignment 2, you're going to start writing your own. And we're going to learn all of the difficulties and, as mentioned, give yourself a lot of time to debug. Because that's probably where you spend most of your time, not writing the code. The writing the code is probably going to be pretty fast, but debugging is going to take a long time. All right, questions on any of that? Okay, so we left off. We were talking about, well, we had talked about the different sort of interfaces that we were going to be using. And so we had left off at deck, and we've seen that deck sort of subsumes stack and queue, right? If I have a deck, I can use it to make a stack interface or a queue interface, and both of them are going to run pretty well. So another interface that sort of subsumes all of the previous interfaces is list. And basically a list is, well, a sequence of things, right? So I have a bunch of things, but they're in some kind of order, not sorted order. What I mean is that there's some index. They can be in sorted order or not in sorted order, but each has a location. I know which piece of data is to the left of it and which is to the right, so to speak. Right, so the list interface, add ix, adds piece of data x at location I. But to do that, I have to shift all data from I to n minus 1 up by 1 index, right? So as we talked about that with the array, I want to add something in the middle, I have to make room for it. Now this is deceptive because I don't mean literally shift. Like it's sometimes the index is implicit, right? Like in a linked list, the index is implicit. If this is at index 2, I know that because it took me 2 steps to get there. Or 3 steps, as the case may be. too, I guess. So when I say shift, I just mean that, well, after this operation, the index of each piece of data is going to have changed, whatever that means for the data structure. It could mean I shift them. It could mean I just inserted a node into a linked list. Get returns the data from location I. Set replaces the data at index I with X, and also this, I believe, returns, let's say the data that was there. So let's call that Y. I'm pretty sure in our implementation we do that. I'll have to double check, but I'm pretty sure that part is missing. A remove removes data from index I, right? So now we're not removing a piece of data, we're removing from an index. And again, I have to shift all the data, whatever that happens to mean. Maybe it means that I just removed a node, or maybe it means that I literally shifted everything. And then size returns the number of data elements being stored in the list. So this list interface is going to be something that we use quite a bit. And of course, our deck, which can be used as a stack or a queue, well, we can sort of simulate all deck operations using the list interface. And you'll find that Java does exactly this in a lot of cases. If you look at, for instance, a deck, it has all of the list functions, but it also has a bunch of deck functions as well. And then, so there's a bunch of, there's a lot of redundancy built into it. And there's probably a push and a pop. And so in Java, you get exactly this. We get interfaces that are sort of the same thing as other interfaces, or at least can be used for other interfaces. All right. Questions on the list? Should be straightforward. Yeah. As what? Sorry. Sorry. No, it can be a linked list, right? It can be any, I mean, so this is an abstraction now. So the list interface means that everything has an index, and so depending on like my underlying implementation, we've said nothing about it. We've just said we're giving a contract right now. Like if I have something at index 3, if I say get 3, and that returns Z, and then I say add 0x, and then I say get 3, well, I mean, maybe I get Z, but I should get what was previously at location 2. And that's sort of I mean, the easiest way to think of it is an array, right? That's probably like mentally, if you're just, it's okay to think of it as an array, but really this is an abstraction. I could implement this any way I want, right? I could do all of this with a hash map if I wanted to, and just store, I could use a dictionary and store each element with its index. And that's, I can implement a list that way. So this is really just an abstraction layer of, we're not saying how we're going to implement this interface yet. We will think of a bunch of ways and look at what the consequences of implementing those ways are. Does that make sense? Yeah. Other questions? Yeah. Oh, yeah. Good call. This should be removed. Yeah. It's one of those things. I should keep a running tally. Otherwise, I'll just forget to fix that. All right. So that's list and queue and stack and deck. They're all kind of related. So now we're going to look at something that is sort of a little bit different, is our set. And set is just for storing stuff. Array list and linked list both implement list. Yes, polymorphism is yeah, a good way to describe it. Yeah, so I can have an array list or a linked list, and those both implement the list interface, and the implementations are different, but the contract is the same, right? If I add something at location 0, I expect everything else is indexed to increment. And however I do that, that's up to me, but Yes. Yeah, polymorphism, that is a good, yes, thank you for that. That's, all right, so unsorted set is just, well, I just want to basically store some stuff. And I want to know that if I've stored it. So the interface is quite simple. I add X, I remove X, or I find X. Now that might seem kind of strange if I have X, you know, and then remove it. Well, why would I want to do that? Or, well, because, you know, maybe I have an index of all the students in my class. And I don't really need to do anything except I need to know who is in my class. I need to know if somebody's in my class. I need to be able to remove people from my class or add them. And maybe not a whole bunch. Maybe I iterate over them as well, but. So what does that mean if I have X and I want to find X? Well, that means that I want to find a Y such that Y is equal to X or equivalent, right? And what does that mean? Well, we are in mathematically, that means that they're equivalent. But when we program, we're going to be using the equals, right? So in Java, if I say something like, if I have two objects, X and Y, and I use the double equals, that is going to compare, what does it compare? Anybody know? Yeah. Let's say these are students. Student X equals new student. Sorry. Well, you get the idea. And then student Y equals new. So what do you mean when you said compares values? So what does that mean? It does not, it, Now I'm kind of so I think what this means, and I might be out of date or, yeah. Right. Well, actually, if we want to, so we're comparing this to say X dot equals Y. So this is how you, in Java with objects, test for equality. But I can do this as well. Right. So the question is, what's the difference between these two things, I guess? Yeah. Exactly. Yes. As far as I know, unless I'm out of date in my Java knowledge, which is always possible. I mean, everything evolves, right? But this compares memory locations of X and Y, which means that I'm testing, is this exactly the same thing? Is this precisely the same object? Whereas here I can have two objects that are equivalent. They're not, you know, they're not, they're not precisely the same object. Maybe they are precisely the same object, but I have some measure of equivalence. Like if it's a student, I might check their student number, right? That's one way to see if these two students are equivalent. They have the same student number, but maybe somebody changes their name or address. And so now I have an extra object, but I want to make sure, like, if these are two the same student, then maybe to like combine these two objects. And so I would use equals. And then I can define, what does equals mean? Well, I define it. Right, so for primitives, this double equals is, you know, I can test if an int equals an int and it's just tests values. But for objects, this double equals tests memory location, which means, are these two things identical? Or I can use dot equals and say, well, are they equivalent? Right, okay, sorry, I guess I missed a message there. So, oops, yeah. So typically, mostly we want to, what did I do here? Mostly we want to do the equals. Occasionally we want to do this, but for our, you know, this is more general because this will return true if the first one is also true. Okay, so we want to find a value or an object y that is equivalent to x, essentially. So when we write it mathematically, we just use the single equal sign, okay, because we are doing this as sort of a mathematical abstraction. But when we do programming, we want to use dot equals for the most part. So that's an unsorted set. I just have a set of things. I want to see if something is in that set or not. And then I can remove or add. A sorted set, I have the same three functions in my interface, but now there's a slight difference in terms of what it means to find something. Now I want to find the least element y such that y is at least x, or return null if y does not exist. So what does that mean? So let's say I had a list of elements, B, D, F, G. And then I say, find C. So I want to find, and let's say it's in alphabetical order, so less than something means before it in the alphabet, right? So A is less than everything. So I want to find the least element y such that y is at least x. So I want to find the least character that comes after C in the alphabet. So find C in this case would return D, right? Because technically C comes, if C was here, it would be right beside D in this list. Or it returns C if it finds it. X is Y. Yeah, all right, that's a good, yeah. So if we use the double equals, then X is Y. Yeah, that's a good way to actually describe it. Nice and simple and easy to understand. Yeah. All right. Yeah. Thank you for that. Okay. So generally speaking, though, when we write data structures, we don't want to know if X is Y. That's not as useful as X equals Y. And in this case, well, we have the same problem or a similar problem. Well, first of all, if we're using the sorted set interface, we have to be able to compare two elements. Now, traditionally, we think of, oh, it's quite easy to compare two elements, right? If they're numbers or they're strings, I can just use less than or greater than. But in Java, everything's an object. So how do we compare two objects? Yes, that's a good point. I sort of skipped over a little bit. So if I said find Z, well, then there is no least element that comes after Z in this list. So this would return null. Yes, thank you. Yeah, that's a good point of clarification. And so why this might be useful is that, well, I have some sorted set and I want to say, well, I want to take everybody, I have everybody's name and then I want to say, take everybody whose last name starts with K through Z. Well, maybe nobody's name actually starts with K, but I still want to be able to find where I would divide that list up, right? So that's where this, in a sorted set, where this find operation would come in handy, where it returns something, even if it's not the thing I'm looking for. It's because I really want to partition my list. Or my sorted set, sorry. Yeah, so this is only possible if there's a total order. That's a mathematical term. So what does that mean in Java? In Java, that means, or for us, it means we implement the compare to function, which actually we implement the comparable interface. So if we want to store things in a sorted data structure in Java, we want those elements to, sorry for my handwriting. We want them to implement the comparable interface, which has this compare to function. And yeah, this total order imposes a penalty on runtime complexity. I guess we're going to cover compare to in the next part. So yeah, we are starting to. So this is for starters. this is most of the interfaces that we're going to implement. Now we're going to see different ways that we can implement them, right? So we have lists and sets and sorted sets. And yeah, questions? It's all very abstract. Yes?
But when you want to sort the elements and you could have sorted set, or you could have list and use collections.sort. Which one do you prefer? To have sorted set or to have a list and then use on it collections.sort?
Yeah, that's an excellent question. And you have to think about that. So what fits into your, and so there's no right answer. It depends on what you're doing. But yeah, so the question is, if I have a bunch of things that I want sorted, should I use collections.sort, which you can do that on an array, anything that implements the list interface, I believe, right? You can do a sort. Or do I store it in a sorted set? Well, that depends. Do I always need these things sorted? Then maybe I want to store it in a sorted set. It's going to be less expensive. Well, as we're going to find out, adding things to a sorted set, that is at least log n time, where n is the size of my data structure. We're also going to talk about what log means, just as a refresher. So adding to a sorted set, that is big O of log n. This is a preview. We're going to get to this. Whereas adding to, say, a linked list or something else is fast if I don't really care about the order in the meantime, right? If I just want to add to the back, it's going to be O of 1 time. But sorting, if I need to sort that, well, that is O of n log n. So what does that, what does that mean? That means as n gets large, it takes longer and longer to do that, right? So if I have to sort, let's say 100 elements, then this is 100 times the log, oops. And usually in computer science, it's log base 2 of n, which is, what's log base 2 of 100? It's roughly, is that it? Yeah. Okay. So 6.7. So this is, let's say 670 operations to sort a list of 100 elements. And I mean, really, if I wanted to compare it to my sorted set, if I add 100 elements, it's still going to take, it's going to take about the same time. But this is how we compute stuff in, what do we mean by analyzing the performance? We mean exactly this, like we're going to pick a operation and then, I'm getting a little sidetracked here. We're going to get to this, but yeah. If you always want it sorted, I would probably say yes. If I just, well, also there's like, let's say my Netflix, I want to look up a show on Netflix. Well, it's going to give it to me in some, I want to sort it in some order, but I wanted to say like genre, right? Well, or no, maybe that's not a great idea. What's a better? Well, let's just, there's certain things where maybe I want to sort people by, maybe I have students and I want to sort them by student number, but then at some other point, I want to sort them alphabetically by name. Well, then a sorted set is not really the best. I want to probably keep it in a list. And then when I know how I want them sorted, then I call sort, right? So it depends on what you're doing. If I always want to sort them in the same order, then sorted set's good. But there's always exceptions. Yeah, these are good questions because these are the things I want you to think about when you're trying to solve these problems. And in general, when you go in your computer science career, although I'm going to qualify a lot of what I say because array list works pretty good in almost all situations, right? Because of the way that computers are structured to actually work well if things are pushed together in memory. So you should always profile things, but there are exceptions to that. There are places where you want to use, where you want to use other data structures. In practice, array list works pretty good most of the time. All right. Uh, yeah. There's a big wind up, there's a big startup, right? We're going to cover generics, which there's just a couple tricky things you have to be aware of when you're programming in Java. And then we're going to cover some foundational math that we're going to be using. So yeah, generics. When you choose a language, you're choosing more than a set of technical trade-offs, you're choosing a community. It's true, right? Like, I mean, people that like C++, they are very technical, detail-oriented. I love C++. But people who love Python are like sort of, like they're the surfers of the programming world. Just, oh man, you just whatever, just use a list. It's fine. But yeah, so you're buying into community. So we've talked generally about interfaces and sort of from a mathematical perspective, and we tried to build a model of the things, what you have to be aware of in data structures in general, but now we're going to dive into some Java specific stuff. So when you do your assignments, some of this might come in handy. So the big problem in Java, of course, as in a lot of languages, is I want to reuse data structures for different types of objects, which easy enough. I could do that in C. It's just not very safe. So I want to do that in a safe way. But let's consider a linked list on ints. And so my linked list has a node that looks something like this. And then, so I'm storing integers, ints, right? A primitive. And I want to make an iterator. So I have an iterator interface. So we haven't talked a lot about iterators. So we'll drop, I guess, some quick advice. Hopefully you know how to use an iterator, but I would use this generally to, I could use a for loop on an array list, right? And just iterate over everything. So I can say something like for int I equals 0, I less than list dot size, and then I plus plus, and I'm running out of space. And then maybe I want to say, and I'm going to use pseudocode here, but print array dot, or list, sorry, list. Wow. List dot get I. Oh my goodness. Keep bumping that thing, I guess. Okay, so I can do that, and this will work on any list. What's the problem if I do this on a linked list? Anybody? Yeah. Well, you can. You can. So let's say we did though. We could, right? I mean, there's a way to do that. And Java does let you do this. Yeah. But yeah, in general, you're right. It's not as easy as you can't do random access. Yeah, so that's true, yes. Yeah, so I think you guys are saying the same thing, is that if I call this get I, well, I start at the front of the list, and then I have to keep walking until I find I. And I have to do that every single time I call that. Right, so iterators are a way to say like, well, if I use iterators on a linked list, it doesn't do that, right? It just says, well, get next is easy. I get the next node and I return the value. So iterators, if you're going to loop over a linked list, you should use an iterator and not this. That will run fine on an array list or anything with random access, but it will be very slow on a linked list. Is there questions on that? Okay, so if you're going to loop in a linked list, use an iterator. Our iterator might look something, we might write code that looks something like this, make a new linked list. I want to write an accumulator. So I'm just going to add up everything in my linked list. And that works fine for integers. What happens if I want to apply similar operations to objects? Right. And so in Java, technically everything, Java has two classes. It has the primitives and the objects. And so everything that is not a primitive is an object, but even our primitives have object wrappers, which you will need to use with generics. So let's say I want to generalize my algorithm. So maybe, what does it mean to add something? Well, that could mean different things for different objects. So everything in Java is an object. I can even represent an int as an object. So I change this into objects, and then I do a cast to integer or maybe number at this point. And then I can store not just ints, but floats and anything that I can add up. But this is getting clunky now. This is clunky, and because we are people, this is error prone. And so what we do instead is we have the compiler do all of this for us, right? So this works, and in fact, this is actually what the compiler does. Makes everything an object and then just casts it to the proper thing. But what we do instead is we use generics, right? So when I make an interface, I insert this in the angle brackets, some token, something that's going to represent a data type, right? So E in this case, which can be basically anything that will compile in this case. And then when I write code, I can say, well, make me a linked list of integers, and then this code will run fine. And well, what the compiler does actually is it takes this code and translates it into this, right? So it gives us back the original solution where everything is an object, but now the compiler is very good at doing this, basically a find replace of all the instances of E with integer and doing the casts in the proper locations and so on and so forth. All right, so when we write code, we are going to write it using generics. But just know behind the scenes that it's just regular old Java that's running on objects and doing casts and then suppressing warnings and things like that. There's no real magic here. All right, questions so far? Okay. There's a couple gotchas to this. All right, so yeah. Well, it gives us, it's nice, right? When the compiler does things, it tends not to make errors. It does reliable type casting. It doesn't, cast it to the wrong thing. Strong type checking. It allows the compiler to do a lot of things in the background that we as people, would take us, our cognitive load would be too high. So we can just focus on algorithms and don't worry about the type checking and casting and all of that. There's a couple of things, I guess, they're not really gotchas, but sort of things that maybe confuse people, right? So if I have a little class hierarchy here, I have a number and an integer which inherits from number and a float which inherits from number. So these pass the ISA test, right? So in this case, an integer is a number because it inherits from number. So anywhere that I use a number, I can substitute an integer. Because it has all the necessary properties that a number does. And same thing for a float. Anywhere that I use a number, I can substitute a float. But when I use generics, I sort of lose, I don't really lose it, right? In this case, if I have a container and I might be tempted to think of the container of integers as being a subclass of a container of numbers, but that's not the case, right? So that when we use generics, I do not get these implicit inheritance hierarchies because of the generics. So that means I cannot substitute a container of integers in for a container of numbers. Those are two different things. So as an example, I have some function foo that takes a container, and the container takes numbers. And so I can take this and I can add an integer because an integer is a number. And I can add a double because a double is a number. And so this will compile just fine. But let's say I made a container called integer, and then I tried to pass it to foo. That's not going to work, right? This does not pass the ISA test. A container of integers is not a container of numbers. So yeah, questions? Sort of gotcha. The other is that we often want to restrict the types of things that we are storing, right? So for instance, maybe I do want to have a container of just numbers because I want to be able to do arithmetic. So I would, in this case, well, yeah. Let's say I did want to make a container of numbers, then I can say, well, if you make a class myContainer and you give it some type t, that t should be a subclass of number. It should pass the ISA test, right? So, yeah. So in this case, if I say t extends foo, anytime I declare a myContainer, the type t that I give it must be either foo itself or some subclass of foo or something that implements the interface foo, right? It has to pass the ISA test. And so yeah, Java, I don't know when the last time you guys used Java was, but Java uses extends for inheritance, and it uses implements for interfaces. But here it uses extends for both. Okay, so extends applies to interfaces and inheritance. We're really deep in the weed. I hope you guys like technical. What's a container? Yeah, so a container is just, well, in this case, it's a collection. But I'm just using it generically. Let's say I made a class called myContainer that contains objects. In this case, it contains objects that must be some subclass of foo or implement the foo interface. So yeah, it's really nothing. It's just a fake class. Yeah. All right. So what is this useful for? Well, particularly, this is useful for sorted collections. So if I want to sort something, well, I can compare, if I'm storing ints or floats or other numbers, I can use these primitive operators, right? The less than or greater than. But typically, I want to store objects. And even an int or a float, I can convert them to objects. So typically, that's what I want to do. So how do I compare two objects in Java? Well, as mentioned, this will return true only if they are, if X is Y, right? If they have the same memory address. To compare arbitrary objects, we use the comparable interface. So I want to make a collection class and I want to store things in sorted order. So I only want to allow the user to store things that implement this interface. And so what I would do, well, okay. So before we get to that, what does compare to do? It returns an int, and that int should be negative if X is less than Y, or positive if X is greater than Y, or optionally 0 if they are equal. Whatever, and again, we're defining compare to, so we decide what it means to be less than, greater than, or equal to. But what this lets us do is, well, if we just ignore this, we get a total order, and if we have this as well, we have a total order with duplicates. Questions? Okay. So how I would use this is, let's say I had a sorted container, right? Again, this is just some arbitrary collection class. I can say, well, this container only works if your object implements the comparable interface. And that way I can make sure it's sorted because I'm going to call the compare to function on these objects. All right. Yes, and as mentioned, the extends here applies, you know, anyway, we covered that already. So this extends is anything with an is a relationship. So T must be an instance of a comparable. There's also this comparator, which means that I can make a separate object. So let's say my object implements a comparable interface. Well, then that's only one way I can sort things. Maybe I want to find a second way to sort them. Well, I can make a comparator object and then just pass that in, right? So very similar, but now both objects have to be passed in explicitly. Let's take a look here at so this collections class in Java is it's a static class of static, basically helper functions that you can use. So if you want things sorted, for instance, I can call collections.sort on my list, right? Or I can call collections.sort on my list, and then I can pass in my own comparator. So that means that don't use there's a traditional way to sort the things in the list I've given you, but just ignore that and sort them this way. So these are the types of things you will, maybe not so much now, although you possibly want to make a comparator for part of assignment 1 at some point when you have to sort things sort of non-traditionally, right? So we're storing strings, but the default way to sort strings is alphabetically. And so maybe we want to define a new way to sort them. One way to do that is to make this, to make a comparator object, right? Or a comparator class. All right, sorry, my throat is getting kind of scratchy, but questions? I'm throwing a lot of technical details at you.
A list of a list can be sorted, right?
Well,
Sort, I mean, sort
Yeah,
function,
yeah.
At least, right?
No, yeah, no, I'm thinking that's a very good question, and I believe that's correct, but the list is an interface. So what that means is that a lot of collections will just implement list, right? So an array list is a list, a linked list is a list. But yes, technically, if I want to sort things, they should be a list. I believe that there might be some small exceptions, but yeah, no, that's a good point. Other questions? A lot of technical details in this class. I'm gonna try and lighten things up whenever I can, but I mean, I feel like I have to apologize. Apparently it's gonna be warm in here, and I'm going to be just like crushing you with math. Sometimes we'll try and keep it a little on the light side. All right, here is just a puzzle. This is okay. All right. So just for fun, don't worry about this, but you will see some of this code in the code that you use. So a linked list, I would implement a node if I'm using generic, something like this, right? I'd say it's a node and it stores a data type T. And then, well, binary trees are similar to linked lists, right? Except now I have like two next, I have a left and a right and a parent. So, I might have a piece of data. And then my left child points to another piece of data. And the right child points to another piece of data. And they both point, so we get this branching effect. We're going to learn how to implement those around assignment 3. So if I'm going to make a node for that, it would look something like this. On your assignment, you'll see something that looks like this. So what is happening here? Well, what we want, or I guess the question is, what is the advantage of doing this over doing this? I mean, what is this? I mean, it's getting complicated, right? So again, you don't have to know this. Most of the stuff that's that's really hairy like this, I'm just going to give you the code and say, this is how you use it. And just use it like this. But if you can consider what this is saying, what advantage might this binary tree node declaration have over this binary tree node declaration? The hint is that one of these, well, this one, works better for inheritance, right? So why is that? What's the specific problem we're avoiding? And by inheritance, I mean that I want to make, so I have a binary tree node, but I want to, for instance, introduce a piece of data, right? So I'm going to make a BST node that extends binary tree node, and then introduce a piece of data. So right here we have a tree node that doesn't store data, but that's okay. We build things up piece by piece. This drove me crazy. When I first started teaching this class, I looked at this and I just went, because Pat wrote this code, Pat Morin. I don't know if you guys know him. Anyway, Pat's he's a very, very smart guy, and but I looked at this and I was just like, I don't know, man. I don't know what this means. So I read up on it and I played with it, and then eventually it still trips me up sometimes. So, any ideas? So what happens if I subclass this and say, so now I want binary search tree node. And so I'm going to subclass my binary tree node just as I did before, but I'm going to use this one instead of this one. Yeah. I didn't quite understand. I think you might be on the right track though, but could you kind of repeat that? I think you're on the right track. It's hard to say, but all right, let's think about what happens. So this node this is not actually a type, eh? This is just a generic. This might as well be T. So these are all you think of it like that. So node is kind of deceptive because there's no class node at this point. And we're down here, so this is a generic, but this is not. This is actually a type, right? This is a class. I've named this class explicitly, which means that if I extend binary tree node using the bottom one, well, my new class is going to have, my BST node is going to have a binary tree node as a parent, and then a binary tree node as a left child, and a binary tree node as a right child. But I don't want binary tree nodes. I want BST nodes. So what this does is now when I extend it into a BST node, these nodes, or in this case, T, let's say, turn into the proper BST node, right? So instead of every time I subclass this, I have a new parent left and right that I just kind of ignore because they're not useful to me anymore. Now, these all become the correct node type. And if you don't understand that, that's perfectly fine, right? It's questions. Okay. One other problem. So we're going to make some array-backed data structures, and with generics, Java is very particular about doing something like this. Java does not like that. That's fine in C++, by the way. C++, it just says, just tries to compile it. Just replaces T with whatever you put in and tries to compile it. It doesn't compile. It's like, well, I don't know, you figure it out. But Java is, I guess, a little more careful, which means that we're a little more constrained. We actually can't do that because Java at compile time may not know what T is. So we have to we actually have to give it a class at that it can track back at compile time, right? So at compile time, it can go back and say, oh, I actually do know what this class is. And I can use that to make an array, right? So we have to do this real convoluted array.new instance, giving the class type and then casting it. This is one of those examples where I just give you the code. It's in a factory class. And so you just use it. And but if you ever look at it, it's going to look like this. And I'm just giving you a short explanation as to why. All right, questions? All right. Compiler voodoo is the best. I'm not sure why Java went that way, but. Okay, so that brings us to math background because, well, we defined the interfaces. We haven't really looked at implementations yet, but when we look at implementations, we are going to analyze them, and to analyze them, we need a little bit of math. Now, this is not a math class, so I'm going to try not to beat you. I love math, and it's fun for me, but I'm going to try not to beat you over the head with math. Hopefully you get some intuition for a lot of this stuff, right? So, and if I ask you any math questions, say on the final, I will tell you up front what they're going to be so that you can prepare. So I really want you to aim for understanding the idea behind this math, and if the way I present it is I get it, man. I've sat in classes where I just like, I forgot what you were saying 5 minutes ago, and now I can't figure out, I can't jump in at this point, right? Once I lose focus, it's over, especially with heavy duty math stuff. So I get it. So try and understand like the underlying intuitions more so than the details. Although we will be going through the details. For those of you who are interested, you can pay attention. Everybody else can kind of like tune out a little. But really, what we want is a toolbox. All of these things are the toolbox, and this is the tool. We want to analyze algorithms and data structures for speed and efficiency and memory usage. Okay, so we're going to review some of these things. Again, not a math class. But these are tools that we will be using. Falling in love with code means falling in love with problem solving and being part of a forever ongoing conversation. It's true. Nothing quite moves as fast as computer science. So if you like computer science, that's great because there's always going to be new things to learn. And then you should, don't isolate yourself, right? Talk to your peers. All right, so exponents, polynomials. We've all seen polynomials. Hopefully you know that 2 to the power 5 means 2 times 2 times 2 times itself 5 times, which is 32. Another way to write this is we might use this notation at some point. I can't remember. Possibly though. I believe this is a capital pi, a Greek letter, but this just means the exact same thing as this. It just means multiply 2 times itself 5 times, right? But this might make more sense when we're analyzing, say, a for loop. I equals 1 to 5 might sort of map a little better than 2 to the power 5. My goodness. So yeah, a to the power b, if I write it like this, it just means a times itself b times. The sort of inverse of an exponent is a logarithm. Logarithms we will be using quite a bit. So you should have a basic intuition behind them, and the intuition is as follows. So log base 2 of 32 equals 5. What that means is that 5 is the number. I take the base, which is 2. What number do I raise it to? That gives me 32. Right? And in this case, the answer is 5. And so I can easily rewrite it like this. 2 to the 5 equals 32. And yeah, it's the answer to this question. So why is this important? And informally, what else does it mean? Well, log base 2 of 32 is informally the number of times I can divide 32 by the base, which is 2, until I get down to 1. Right? So how many times can I divide 32 in half before I get to 1? Well, 32 divided by 2 is 16, divided by 2 is 8, divided by 2 is 4, divided by 2 is 2, divided by 2 is 1, so that is 1, 2, 3, 4, 5 operations. And so yeah, questions? Okay, so why is that relevant to computer science? Well, there's a lot of divide and conquer in computer science. Let's take binary search as just a simple example. Binary search, I have a sorted list and I want to find something. Well, I can do something a little bit easier than just look at everything. I can say, since it's sorted, I could say find, K. So I look at the middle element and I see that it is an O. Well, O comes after K in sorted order. So that means I only have to look over here and I can ignore everything over here. Right? So if I do a binary search, every time I start with n elements, every time I look at an element, I can eliminate half of them. So I divide my problem size space in half. And so how many times can I do that? Well, I can do that actually log base 2 of n times. So the logarithm tends to be small, but it's basically any time I divide my problem size by some constant fraction, often 2. The answer to how many times I can do that is a logarithm. All right, questions? Okay. We can also do some fancy stuff, right? Since it's the inverse, I can raise 2 to the, if I do this, basically the 2 to the power log base 2 cancels itself out, right? And I'm just left with 32. So these two things cancel out, and then I end up with whatever's left. In computer science, if we omit the base, then we assume log base 2. Not, 10 would be what you learned in high school and grade school, but in computer science, it's log base 2 almost exclusively, especially for computer science operations. But basically, any base is valid because if we change we can change the base of a log, right? So log base A of C. Let's say that I wanted to change that to a log base B of C. Well, I divide that, log base A of C is multiply times log base B of A, and I get, here, let's look at an example. Let's say I wanted to change log base 32 to log base 10. Well, I guess I kind of did it backwards here, but log base 10 of 32 would be equal to this. The important thing to note is that the difference between this base and this base is a constant fraction, which means that logarithms basically grow the same, right? In computer science, we are often concerned with, log base 2 of n, and let's say log base 10 of n. Well, what does that look like? As n gets bigger and bigger, we can describe it using some function, and we often do. And the function looks something like this. And basically, log base 2 of n and log base 10 of n look pretty much the same, right? So they grow at about the same rate. So we can substitute one log for another, and we don't really care. In terms of the asymptotic analysis, they're roughly the same. So when in doubt, it's log base 2, but any log is pretty good. A very fast growing function is a factorial. So 5 factorial equals 1 times 2 times 3 times 4 times 5. This might actually also come up. And as that number gets bigger, this really, as the n gets bigger, the resulting gets really, really big. And in general, n factorial is 1 times 2 times 3 up to times n. We may run into binomial coefficients. Again, very lightly. If you've taken 2804, you've seen all this before. If not, well, this is called 5 choose 2. We can write it using factorials, but don't worry about it. Just don't waste your cognitive load on this. All right. Sorry. I just really like that picture of the cognitive load. It's so I've stared at that for years and never got it. And then just finally before this class, I was like, wait, I think I understand what that picture means. But yeah, what this means is that I have a set of 5 things. The 1, 2, 3, 4, 5. How many different ways can I choose 2 of them? This is called, this is called a binomial coefficient. How we would say this though is 5 choose 2. And it's the number of ways that I can choose 2 elements. So I can say, well, I can choose 1 and 2, that's one way. I can choose 1 and 3, that's another way. I could choose 1 and 4, that's another way. And so all possible combinations, well, it turns out there's 10 of them. There's 10 ways I can do that. And that might come up at some point. In general, n choose k is defined like this. You don't have to know that, okay? But, you can punch that into your calculator. It will give you the answer, which you might be interested in. Summations. So when we run algorithms and data structures, we often use loops. And when we express these things mathematically to analyze them, we often use the summation. So this is the notation. This is the, what's this called again? This is some Greek letter. Anybody remember their Greek yet? Sigma notation, that's it. So this is a sigma, and this is called sigma notation. So let's say we had a function f, and it could be, this should really be f at I, and f at I can be any function. So function just returns some value. And then I'm going to just sum up all the values that get generated. So for example, if my function f sub I is equal to 5, that means no matter what value I put in, I get back 5. Then this is I equals 1 to n of 5, and I would sum 5 plus itself n times. And that would be 5 times n. Right? So this is going to come up a lot, this sigma notation. So a couple tricks to using sigma notation. Well, here we can express it as I equals 1 to n, and that means that I'm iterating n times, and that's easy. But of course, computer science, we often start our for loops at 0, right? So I can also write this as this, and these are the same thing. It's 5 added to itself n times. But here we're starting at 0 because that's what for loops do, generally speaking. All right, there's a bunch of operations we could do to summations, right? We can split them. So if I have I equals 1 to n of 5, I can change that into, well, this is 5 plus 5 plus 5 n times, right? But that's also, I can write that as 2 plus 3 plus 2 plus 3 n times. And then I can split those into their own summation. So I can do these little tricks to help me analyze things. I can sum up all the values from 1 to n, right? So that actually has what's called a closed form. So sigma notation is technically not a closed form. And what does it mean to be a closed form? Generally speaking, or sort of informally, it means that this is a form I can punch into a calculator and get back a value. This one, not so much, right? If I had a fancy calculator, sure, but this is something I can compute directly, and this is something that I would have to run a little algorithm to compute. All right, closed form. So this closed form comes up quite often. We will see it a couple times. Yeah, all right, let's quickly go through these just as an exercise. I equals 1 to n of 5 times I. Well, what I can actually do is, this is 5 times 1 plus 5 times 2 plus 5 times 3. But let's say that, well, everything has a common factor of 5, right? So I can take 5 out as a common factor and say that's equal to 5, 1 plus 2 plus 3, etc., up to n. Which means that I can just take 5 out as a common factor in my sigma notation. right? So when I have something that, when I have a common factor between all of my elements that I'm summing up, I can just take that out. That's equal to 5 times the sum, I equals 1 to n of I. And then, well, that has a closed form, which we saw, right? We're not going to spend a lot of time on that, but that is equal to the closed form of I equals 1 to n of I is n times n plus 1 over 2. And so, yeah, I can convert this into a closed form using a couple tricks, which we will see. I can do something similar over here, but I can, of course, split this into two sums. I equals 1 to n of 5 plus I equals 1 to n of I, and that is equal to 5 times n plus the closed form. All right, now this is, if you're interested in this stuff, that's great, follow along. I'll ask questions. Hopefully you guys can help out. If this just, it's too much, it's too hot, you don't care about math, it's okay. Just try and get the intuitions, right, behind some of these things. But this is a tool. We will be doing stuff like this when we analyze algorithms. Questions? All right. A harmonic number, a few more things, and then we'll end for today. The harmonic number also comes up. It's this particular sum, I equals 1 to n of 1 over I. It looks like this, and it is it has its own name because there really is no closed form for it. But there is a good approximation. The nth harmonic number is at least ln of n and at most ln of n plus 1. Ln of n is the natural log, right? So the log-based e of n, where e is Euler's number, it's an irrational number. So it goes on forever. But it's roughly, it's a logarithm, so it's roughly equivalent to log base 2 of n. This will come up in some of the things that we look at. Probability, you should know, you're going to have to know a little bit of probability. I'm going to go through it formally, but you should just understand informally. I flip a coin, it's a fair coin. My probability of it coming up heads is half the time it's going to come up heads, right? That should be like, that intuition is going to serve you pretty good. Okay, I will use formal notation and all of that, but we'll also try and keep it a little bit informal. It's a set, it's known as a probability space. This is the set of events that can happen when I flip my coin. It can come up heads, it can come up tails. This is a uniform probability space because these are both equally likely. Right, so the probability of heads is 1/2, the probability of tails is 1/2. So we tend not to use percentages or things like that. We tend to use a value between 0 and 1. So probability, if the probability that it comes up heads is equal to 1, that means it's definitely coming up heads. Right, so each probability is some value between 0 and 1. And when you sum up all of the probabilities, these should sum to 1. Don't worry too much about that. Yeah, you should know if we roll a fair die, the probability of each of those outcomes is 1/6, right? Simple, but also you might want to know, well, what's the average? If I roll the dice and I take the value every time I roll that die, and then I did that 1,000,000 times, and I divided by 1,000,000, what number will I get? Anybody know? Yeah. No. I think he misunderstood. I think he misunderstood the question. Yeah. No, it's you're answering a different question. So the average value. I mean, 3.5. Yeah, exactly. Yeah, sorry. So yeah, on average, it would be 3.5. So basically, as I perform this experiment more and more, it's going to get closer and closer to the average. But if I roll the dice once, I would expect on average to get well, I can't get 3.5, but if I did that experiment a million times, it would average to 3.5. And you can determine that pretty easily, right? I just sum up all the possible values and divide by 6. And that's known as, that's known as the expected value of X. Or X in this case is the value of the dice roll. And so there's some fancy, this is the actual definition of expected value, but expected value is just the average, especially if it's a uniform probability space. When this comes in handy is when it's not a uniform probability space. Like maybe I go to Vegas, I want to cheat, I have a die that comes up 6 more often than not. So then that changes the probability and it changes the average, right? So if I have a die that comes up 6 every third roll on average, then it's going to skew my average higher. And so this formula takes those probabilities into account. But expected value is just an average. Think about it, if I perform this experiment a million times, what would I expect to get back on average? All right, I guess we're going to stop there today. So yeah, I'll be around. Technically, this is officially office hours, so feel free to ask questions. I should have some company arriving shortly. And I'm going to keep the Zoom session open. I'm going to stop recording, but